backstage.
So, oh yeah.
Like in Hollywood.
For costume changes and stuff?
Yeah.
Yeah, that's a good idea. Okay, just a second ago we talked about orbital velocity. We also talked about, earlier, we talked about escape velocity. So orbital velocity, just a reminder, we just came up with that equation. It was mg divided by r, and the escape velocity we talked about was equal to the square root of 2mg over r. Just a reminder about that. It's kind of making the connection to our previous topic. Kinetic energy is too low to escape. You still have zero energy. If you had bigger speed than that orbital object by a root 2, therefore your kinetic energy would be twice as big, then you could escape. That would be that velocity there. Let's come back to this idea here of the orbital velocity, and I want to actually talk about that in a way that seems more logical or a more natural way of talking about orbits. When we talk about orbits, we don't generally talk about the Earth moves at 30 kilometers per second around the sun. We don't really say that. Normally we say the Earth moves around the sun in
a
year, and then we talk about the distance, right? So really, the more appropriate way of talking about orbital velocity would be to connect orbital velocity to two concepts, I mean the period t and the radius r, right? Those two things, and if we have an orbit, so for example the sun, right, and there's our Earth moving at a certain speed VO, how is VO related to r and the period? What you got there?
I don't.
Can you repeat what you just
Sure. How is the orbital velocity VO that the Earth is moving at related to the period that is the time that Earth takes to orbit the sun, or the time that a satellite or a moon, which is also another word for satellite, right, orbits the planet, and the radius out orbit? How are those connected? Yes, that's
V equal V orbital like times the radius or something.
so. Orbital velocity is a velocity, a speed. Speed is equal to distance divided by time. We're looking at how far does it go divided by how long it takes. Viola, how far does it go?
2 pi.
2 pi r. So we have 2 pi r, and this one over here, yeah, the time is of course t. So we can say VO is 2 pi r over t. So we have this expression here, and we can of course connect this here to that. Okay, if we do that, and just a reminder, this came from the gravitational force being equal to the mass times the centripetal acceleration. If we now plug this in there, okay, we would get 2 pi r over t is equal to the square root of mg over r. Let's move this over in this direction. To mush this thing together, what do we have to do? What would be actually helpful here? Do you like the square root?
No.
I don't like the square root either. How about we
Let's
just
square
square
both
the
sides.
whole equation? That sound good? Let's square the whole equation. We're going to move this thing over here. Left side, 4 pi squared r squared over t squared. That's equal to mg over r.
I don't like that either, though.
You will like it in just a second. So we're going to actually use this equation in two different ways. We're going to move over here, one version of this, then we're going to move over here, the other version. The one way we're going to use this is by solving it for the mass. If you solve this for the mass, you would get that the mass of the central object, if it's an orbit of a satellite about the Earth, that could be the Earth, or if it's a moon going around the Earth, that would be an example of that, or if it's the sun, that's the central object. The mass of the central object is equal to, let's put the constants together, okay? The constants, of course, being 4 pi squared and then we have g, and then we have r cubed over t squared. Okay, 4 pi squared r cubed, and then we have g in the bottom and t squared on the bottom. That is an expression for the central mass. And of course, if you're not geeked out by this, you're not paying attention, because this means that if we know the time an object spends orbiting a central body, and we know the distance that orbiting object is from that the central body, we can figure out the mass of that. We can do that for the sun in just a second. Actually, just a second, meaning right now. Let's do it. Okay, so for our example would be, let's do this for our Earth, for our sun. Have we done this? No, we didn't do this.
We did it for the Earth, but not for the Sun.
Okay. Oh, we did for the Earth. Okay, cool. So let's do it for the sun. We would say the period is about pi times 10 to the 7 seconds. It's 31.5 million seconds in a year. And then the distance that we are from the sun is 1.5 times 10 to the 11 meters. If we plug those values in, we should be able to get the central mass. The mass of the sun, symbol for the sun is a circle with a dot in it. If we plug the values in, we get 4 pi squared over g times r cubed, that's 1.5 times 10 to the 11 cubed. You could write down t as pi times 10 to the 7. The pi's would cancel, you nerds, which will be fun, but we can also leave it in there 3.15 if you want to type into your calculator. Either way is fine. 3.15 times 10 to the 7 seconds. We're leaving the units off because of World War II, as mentioned earlier. So, punch it in. I'd use my phone, but it's recording this right now.
Can you, yeah, can you, thank you.
You're the quickest
Yeah.
calculator typers in this
I'm
room.
writing down the equation yet.
I don't think I have that with me today.
Wars.
Alrighty, let's go women in STEM. What you got?
Nothing at the moment. My calculator just turned on.
Oh, booting up. Just a second.
Can't read it.
It's not Jacob here, it's
Oh, G. You need G as well. G is 6.67 times 10 to minus 11. I didn't plug it in, did I? I can try if I put that in there here. So we can put that actually in there. There we go. 6.67 times 10 to minus 11. I'm leaving all the units off. There we go. All right.
Here, let me find my calculator. Got it.
There we go.
Turning on. So, okay.
All right.
Oh, wait, this is, alright.
We can always cut this out when you actually post this on YouTube.
So I'm gonna post it on YouTube.
0.013.
We'll go with that.
2.
What'd you get?
That's a very small sum.
Oh, times 10 to the 30.
Good. 2 times 10 to the 30 kilograms is the mass of the sun. Cool. That's super exciting. There's another way that we can do this. We can say, of course, if we know the mass of the central object and it doesn't change, well, guess what? For all the planets, the sun doesn't change. It's always the same mass. We can also say, we'll rearrange this to now consider the central mass constant, and it is. Okay? And then we can actually say, we're going to, oopsie, sorry, I put the arrow in the wrong place. Sorry about that. I meant to say, we're going to take this original equation that we had, this green one, right? We have the red equation there. But we could also come over here and say, okay, we'll consider actually mass also a constant. And we're just going to look at these two things as our non-constant devices. If you want to think about it that way, we can say that r cubed over t squared is equal to mc times g divided by 4 pi squared. And that's a constant for the same central mass. So all planets will have the same ratio of r cubed to t squared orbiting the sun. All satellites will have the same ratio, r cubed over t squared for the Earth because the central object stays the same. Okay, so we could say this is equal to, obviously, a constant. That making sense? Yeah, because all these things are constant. The central mass is constant, g is constant, 4 is constant, pi is constant. Now, we're going to go one step further and actually calculate this value very quickly and easily. Why are we going to calculate it easily and quickly? Because we're going to say r cubed over t squared. We're going to use special units for r and for t. We're going to say, what if we measured r in AUs? You might ask, what is an AU? An AU is the distance, on average, of the Earth to the Sun, an astronomical unit. So we're going to use this number and call that an AU, all right, as our standard unit for measuring distances in our solar system. So instead of saying the Earth is 150 million kilometers away from the Sun, we can say the Earth is 1 AU away. Instead of saying Jupiter is 700 million kilometers away, it's 4.5 AUs away. Make sense? Much easier to talk about it that way. We do the same thing here because saying 31.5 million seconds for the orbit time of the Earth is stupid. We obviously say it's 1 year. Exactly. We're going to use time in years. And if you're not getting geeked out, you're not paying attention, as I mentioned earlier, that means, of course, that for the Earth, r is 1, right? For the Earth, t is 1, which means, of course, that this ratio, 1 cubed over 1 squared, that's just equal to 1. So in our solar system, the ratio of r cubed to t squared for all planets is 1. Okay? It's always going to be equal to 1. Technically 1 AU cubed per year squared, but we can super easily use this to figure out distances or orbital times. Let me give you an example. Our Saturn is about 10 AUs. Okay, it's true. It's 5, 10, 20, 30. Easy to remember, maybe. 5 is Jupiter, 10 is Saturn, 20 Uranus, 30 Neptune. If we take this number and plug it in to r, we get 1 is equal to 10 to the cubed divided by t Saturn squared. And that's, of course, easy to solve for the orbital period of Saturn. So TS, you can figure it out from that equation. So solve it for TS and find the value. Based on that number, it's pretty close to being correct. I think it's 9.6 or something like that. Nicht alle auf einmal.
Hang on, my calculator's gotta turn off.
Yeah.
Oh wait, that's just 10 cubed, right?
Yeah, it is 10, so it's 1,000.
Yeah, I don't need my calculator for that.
Okay, but for the square root of 1,000, you probably need it.
Oh, true.
Yeah, that's true. It's 31.5.
So I don't need it then?
I don't know. You can try. Is it maybe not 31.5?
Yeah.
Is it 31.7?
It's 31.6.
Okay, sorry. Yeah. So 31.6 years. There we go. So that's interesting. I mean, Saturn is 10 times as far away from the Earth, from the Sun as the Earth, but it takes 31 times as long to orbit. So that's a relationship. And of course, you could use it the other direction. This law here is Kepler's third law. So Kepler was not a good theoretical physicist, but he was very good at analyzing empirical data, and he came up with his laws by basically just analyzing the observations by Tycho Brahe. You might have heard of him. He was Danish, I think, and he had all these observations of the planets, and he used that data to come up with the laws, but he didn't know why. He just empirically he found them, but he didn't explain them in terms of physics. Newton did that later. So that's kind of the sequence. Tycho Brahe came up with the data, Kepler analyzed this, and then Newton came up with the theory behind it. So if they all put this all together and wrote a paper about it, and they were still alive, they might get a Nobel Prize for that, but they're dead.
That's unfortunate.
Yeah, well, I don't know. Is it? I mean, they'd be like 500 years old by now. That'd be kind of weird.
Do they have like a,
There
do
was
they know
no
where they're
original.
buried? Because we could like make a fake Nobel Peace Prize, or not Peace Prize.
Yeah, Newton is, yeah, I've been to Newton's tomb. It's in London. He's buried in Canterbury Cathedral or Canterbury Chapel. Well, anyway, he's in one of those, yeah, right across from the, yeah, I think it's the chapel, I think. Also where they have some of the royal weddings and all that stuff. Anyway, cool. That makes sense. Now, Kepler's third law. Okay, so I'm assuming you're thinking about what the other laws are.
I actually was.
Okay, good. Okay. So there's 3 laws that are important. All right. So here we go. So Kepler's first law. Kepler's first law. And this is actually an important difference. Orbits are ellipses. This is a slight difference. So orbits are ellipses is an important statement. They're not circles. Of course, circles are also ellipses, right? With eccentricity 0. But anyway, the point is orbits are all ellipses. And we're going to talk about that in a second, but it's an important observation. Previous astronomers thought they were circles, and that affected actually the data. It didn't work out perfectly right because they're not perfect circles. So the math's not going to work out. So we figured out they're ellipses, that's important. Like Copernicus thought they were circles, okay, for example. Kepler's first law. And then we have Kepler's second law.
So just like spend all this time stargating or what?
And Kepler's second law says, and this is a little bit complicated, planets sweep out equal areas in equal time. And let's make sense of those 2 statements together. We can make good sense of these 2 statements together if we think about an elliptical orbit. So if we think about an elliptical orbit, so we've got a central object, here's the sun, and we've got an orbit that looks kind of egg-shaped. Okay? And we have over here maybe a planet that's over here moving in this direction. And that's the speed at that time. Okay? So it's moving in that direction, and it moves a certain distance in a certain time. So it moves maybe from here to here, let's say in a month. It doesn't really matter. Okay? So let's say this is the area swept out in 1 month. 1 month area. Okay? Now what happens to this planet as it's moving towards the sun?
It gets closer, the area gets smaller.
It gets closer, that's true. And what's the other thing that happens?
It moves slower,
It-
faster, slower. Wait, slower.
Okay, you're
faster.
if you want to throw same speed
It's
into
gonna
that
move
matrix,
slower
you're
as it's
carpet
closer
bombing
to
all
the sun.
possible answers. But which one is the
No,
correct
faster.
answer?
So we think it's faster,
It's going to be faster. And why is it going to be faster?
so that it covers the same amount of like.
Oh, okay. That there's no causal relationship there, but
Yeah, but
we explain it that way. But why does it become faster? Yeah?
because it's like closer to the sun, and then like the gravitational pull makes it like.
The gravitational pull is actually in this direction. Think about it. We talked about this, right? The gravitational pull at this time is in this direction. That's Fg. And take a look what direction Fg is compared to V. We talked about what kind of forces do what kind of work. Okay? And what kind of forces do positive work. Relative to the velocity, they have to be acting forwards, backwards, or sideways. Forwards. And this force is forwards. It's just slightly forwards, right? Because it's moving in that direction, the force is in that direction. So at this time, it's already making it faster. And of course, as it gets closer, so for example, when it's here, right now it's moving a little faster. And at this point, the force is even more forward. And also a little bit bigger. But the point is that as the planet, or whatever this is, satellite, approaches this central orbiting central object, it becomes faster because force of gravity is doing positive work, ergo making the kinetic energy bigger, therefore making the speed larger. Okay? And of course, if it is moving faster, for example, once we are at this location, it's moving faster than it was moving before. So that means it's going to, yeah?
No, this is a different question.
Okay, so that means at this point it would actually not only move that far, but it might move this far. But it would move a bigger distance on the orbit, and that means, of course, that the area here could be the same in this month. This is again 1 month here compared to 1 month here, and then as it's right on the back end, okay, as it's at the closest point to the sun, BT dubs, that's called the perihelion, the closest point to the sun. The furthest point over here will be called the aphelion. Okay, aphelion is the point where it's furthest away, perihelion where it's the closest. Over here, it's going super zippy, right? Super zippy is speed. We're going to use fuchsia, hot pink, whatever, for super zippy. So at this point, that's fast. Okay, that means in 1 month it might go like sweep all the way around here. It means even though oh sorry, there we go. I forgot that one. Okay, so the area would be the same again in 1 month because it's zipping around. Okay, good. Those are the Kepler's 3 laws. We also introduced how to use t squared over r cubed equals 1. And there we go. Cool. Let's stop the video again so we have another spot to kind of, we're almost at the end of the class anyway.